Hello everyone, welcome to PhD Lecture 6. Today we will discuss about faults analysis, in particular symmetrical faults. We will discuss two methods. The first one is Thevenin's equivalent circuit and the second one is the focus, how to use impedance matrix Z-bus to analyze a fault. And finally, we will discuss about a new definition of short circuit capacity or SSC. So talking about faults in a three-phase circuit, mostly is between the phases or it's between the phase and the neutral. The main cause of faults coming from the insulation breakdown, lighting activities mostly, or wire sticking together because of the wind or animals or plant make any physical contact with the wire. When the fault happens, high currents occurs and it must be detected and deal with using circuit breakers to protect our devices. When we do the fault calculations, usually we neglect the resistance of the network and the load current because of the fault happens very quickly and therefore reactance has much bigger impedance here. Talking about the reactance of the line usually stay constant, but the reactance of the generator, for example, or the load will varies a lot. Therefore, we have the definition of the subtransient reactance, transient reactance, or steady state reactance. How to select the reactance? It depends on the application, but for fault analysis, usually we use the subtransient or transient reactance. About symmetrical fault, the fault happen quite rare. Um, Only 2 to 5% of the system fault are symmetricals, and the analysis of the faults is the most simple, it easiest, and usually it's carried by per phase basis. When the faults occur, the system remains balanced, but this results in the severe damage to the electrical power. The fault represents an addition of fault impedance at the fault location. If the fault impedance is zero, then the fault is known as voltage fault or solid fault. So when we talk about fault analysis of a symmetrical fault, we usually use Thevenin's equivalent circuit as a direct method. First, we need to calculate the pre-fault bus voltages, and then we convert the network loss into constant impedance. And after that, Thevenin equivalent circuit from the fault bus is obtained using Thevenin's theorem. So after applying the theorem, the change in the bus voltages are obtained, and then the bus voltages are obtained later by the superposition of the bus voltages. When we know about the bus voltages, the fault current in the branches can be found using simple circuit analysis. So first, let's talk about a very simple numerical example. We consider a power system. So in this figure, the generator are presented using transient reactance and the other reactance such as reactance from transformers and transmission lines are represented using PU values. The other components like shunt capacitance and resistances are all neglected. So in this case, we consider a three-phase fault balance with the fault impedance of 0.15 pu at bus 1 and later bus 3. We need to find the fault current and bus voltages and line currents. So let's talk about the fault at bus 1. The pre-fault bus voltages can be obtained from the power flow solution. But let's consider the free flow bus voltage when there is no load. So in that case, there's no current flow at all, and therefore the uh, voltage at bus 1, bus 2, and bus 3 are on 1 pu, and they are noted at V10, V20, V30. 0 is for initial condition. The flow is simulated by switching on an impedance ZF or Z4 like this at bus 1. So before the flow, the circuit breaker is open, and after the flow, we close the switch. The Thevenin's theorems state that if we have a circuit like this, we can replace the circuit with a Thevenin's voltage source, and then other circuit components like voltage sources will be 0, and then we close the switch, and the current that flow through the fault impedance here will be the result of this equivalent circuit. So in this case, the Thevenin's voltage is equal to the voltage at bus 1 before the fault, which is VTH equal V10, and in this case it is 1.0 pu. The Thevenin impedance is defined as the impedance viewed from the faulted bus, or bus 1 here. So looking at bus 1, you see that the impedance here is actually this branch in parallel with this branch. And we can start from calculating the equivalent impedance of this part. And Z equivalent here is Z12 in parallel with Z31 in series with Z23 like this. And in the end, we have Z equivalent equals J 0.3733 pu. So after that, we can rewrite the equivalent circuit like this. And now we can see clearly that the impedance looking from bus 1 is from a branch here in parallel with this branch, and the impedance looking from bus 1 is Z11 equal 2 branch in parallel like this. And in the end, when we put the Z11 into the simplified circuit like this, we have a Thevenin equivalent circuit, and then we just connect it to the fault impedance via this circuit breaker. This simulated one, it doesn't exist, but we just put there to represent the fault. After we close the switch, fault current will flow, and we can calculate this by simply divide the voltage over the total impedance. Notice that when the fault current flows, the voltage on the bus 1 will reduce accordingly, and we can calculate it in this case, and then using the superposition theorem we can calculate it back to obtain the real bus voltage during the fault and also the other currents during the fault. Notice that we should look at our original circuit as well as our equivalent circuit. Next, we look at the fault when it's happened as bus 3 like this. We simulate the fault by switching on an impedance ZF or Z fault here at bus 3. Um, the analysis in general is very similar to the first case. However, in this case, it's quite tricky because the line between bus 1, 2, and 3 is form a delta connection, and it's not so simple to calculate the equivalent impedance looking from bus 3 anymore. But here we can use the delta to y uh, transformation. So we can convert this to a so the fault analysis method using Thevenin is quite straightforward, but it's not so convenient when we use that method in a very complex system. Instead, we can use the second method using impedance matrix ZBus. It is particularly useful for large systems with a lot of complexity. So in this case, it is more practical and very easy to use. All the voltages and impedances are expressed in PU values, and then we consider a n-bus system um, in a balanced three-folds, which is initiated via the bus number kth through a pole impedance Z-fold. We assume that the pre-fold voltages are given in this vector V10, V20 until Vno. So we go straight into numerical example number 2 to see how we can build up a impedance matrix in the example 1 with a similar circuit. So we begin with calculating the admittance matrix Y bus. The admittance matrix Y bus for in this case of a 3 bus system is a 3 times 3 matrix, and it is like this. So you can see that it is a symmetrical matrix. The non-diagonal components are given as yij equal yji equal minus yij, which is the admittance between bus I and bus j. In this case, for example, looking at bus 1 and bus 2, the admittance between bus 1 and bus 2 is 1 over Z12, and therefore Y12 equal Y31 equal minus 1 over Z12. The same apply for um, the component between 1 and 3 and the component between 2 and 3. How about the diagonal elements here? It is the summation of the admittance that is connected from other nodes to the node that we are talking about. So when we talk about the other nodes, we calculate from the neutral or ground as well as from the other buses. So for example, Y11 here, the element equal to the admittance from the neutral to the bus 1, which consists of the generator and the transformer D1 in series. So the admittance from the neutral to bus 1 is given as 1 over ZG1 plus ZT1, like this. And then we add the admittance from bus 2 to bus 1, 1 over Z12. And then the admittance from bus 3 to bus 1 over Z13. The same applied to bus number 2. So we have the admittance from the neutral or ground, then the admittance from bus 1 to bus 2, and then admittance from bus 3 to bus 2. About bus 3, we don't have anything connecting from the neutral, so we don't have any admittance shown here. Instead, we have only the admittance from bus 1 to bus 3 and bus 2 to bus 3. So in the end, after calculation, we obtain the Y bus look like this. Notice that because of this simple construction, if we have this Y bus given, we can rebuild this the original circuit by looking at, for example, the non-diagonal elements. The non-diagonal element immediately gives us the impedances between the buses, and then the remaining diagonal components will give us the remaining impedance from the bus to the neutral or ground, which is the sum of these impedances. We will discuss it in more details in our seminar, but from these equations and formulas, we can see that it is very easy to form a Y-bus matrix from a circuit, and in reverse, it's also simple to build a Y-bus, to build a circuit from a Y-bus. So after obtaining the admittance matrix Y-bus, the impedance matrix Z-bus is simply the inverse of the Y-bus matrix. When the fault occurs at bus K via Z fault, the fault current is given by this formula. I fault in the bus K equal the voltage at bus K before the fault divided by the element KK from the Z-bus matrix plus the Z fault. To get the fault voltage as the bus number I, for example, we can apply this formula. Vi at fault equal the Vi0 or the Vi before the fault plus the Z-bus number IK multiplying with the fault current that we just calculated here, and then we can rewrite it in this form. After we obtain all the voltages at the buses during the fault, we can calculate the branches current during the fault using this formula. I fault during the fault from node I to node J equal the voltage at bus I during the fault minus the voltage at bus J during the fault over the impedance between bus I and bus J. Notice that this impedance is the impedance in the circuitry, not the impedance in the bus in the Z-bus matrix. So in this example, we can calculate the Z-bus via inverting the obtained Y-bus matrix, and after that we can get this matrix. When the fault occurs at bus 3, we can use the formula to calculate the fault current as follows. The current fault at bus 3 equal the voltage at bus 3 before the fault over Z bus 33 plus that fault. Z bus 33 here is this one. And as a result, we have the fault current equal to minus J times 2.0149 pu. About the bus voltages during the fault, we apply this current, and for example, the bus voltage at bus 1 during the fault equal the voltage at bus 1 before the fault minus Z bus 13 over Z bus 33 plus Z fault multiplying with the voltage at bus 3 before the fault equal 0.7284 pu. And after that, we can obtain the bus currents during the fault using the formula given before. For example, the current between bus 1 and bus 2 during the fault is given as the voltage at bus 1 minus the voltage at bus 2 during the fault, everything over Z12. Notice that this Z12 coming from the circuit, not from the matrix. Is from here. And in this case, I12 equal minus J 0.0662 pu. And finally, we discussed about short circuit capacity SCC. This is the short circuit quantity in the mega VA, and it is used to measure the strength of a bus, and it's also used to determine the dimension of a bus bar and the interrupting capacity of a circuit breaker CB. According to the definition, the SCC equal square root 3 of the line to line base voltage multiplying with the short circuit current. Usually it is shown as mega VA. You can see that this one is actually the power of a line in a nominal condition with the maximum voltage and the maximum current, and it shows the maximum three-phase power in this case, and it is applicable for choosing a circuit breaker to deal with that kind of fault. So this is the end of our lecture. For your homework, please review mathematics, and also please review the PU system which was discussed in lecture 2. After that, you can practice tutorial 6. Remember also to practice how to build Y-bus and also how to rebuild circuit from Y-bus. This is not included in tutorials, but it will be included in the final exam.